Hello once again. Today's notes are on exponential and logarithmic equations. So today we're going beyond simplifying expressions to actually solving equations. And today we're going to see exactly why logarithms were developed in the first place. I know many students do not care for logarithms. However, I want to demonstrate to you the reason why they were even invented. Why do we even need these things? But before we do that, just a few more expressions to simplify. First one here says the log base a of a to the x power. What is this equal to? Let's think about how these exponential and logarithmic functions work. This is like saying a to some power equals a to the x power. Well, let's think about that. A to what power equals a to the x power? Well, that power is x. So this whole expression here is equal to x. Likewise, down below, a to some power equals x. And this is saying, what is a to some power? Well, that's also equal to x. So these two relatively complex looking expressions, both simplified to just the value x. Okay, not something you absolutely need to know, but you may see some expressions kind of like this. This might help you simplify those. Okay, let's move in. Now, before we even get into our first example, there's a warm-up problem. So here's a warm-up. 2 to some power equals 64. Well, you can probably do some of this thinking in your head, thinking 2 times 2 is 4, times 2 is 8, times 2 is 16, times 2 is 32, times 2 again is 64. So we did that with 6 different 2's, so x equals 6. Not too hard to do. You probably could have done that in your algebra days. However, what if we have something like this? 2 to what power equals 60? So using that trial and error method, like 2 times 2 times 2, well, 2 to the 5th power equals 32. 2 to the 6th is 64. So we know x is going to be a little bit less than 6, but what will it be exactly? Now you could use your calculator to kind of guess and check at something close, but this kind of problem where x is your exponent is impossible to solve algebraically without the use of logarithms. So really it was to solve this kind of problem that logarithms were even developed. Okay, so how do we do this? What I'm going to do, I just want to rewrite the problem. 2 to the x power equals 60. Now one thing we can do is we can take the logarithm of both sides of an equation. Just like you can add 5 to both sides, you can also take the logarithm of both sides. Once we do that, remember we have a property that says if you have a power, you can bring it in front of your logarithm. That is huge for this kind of problem because the difficulty up here was we didn't know how to deal with this power. Now we can rewrite this so it's not a power at all. It is now x times the logarithm of 2 equals the logarithm of 60. And to solve for x, we can divide both sides by whatever this logarithm of 2 is. So let's divide both sides by the logarithm of 2. On this left side, those are gone, so we have x by itself. So we have x equals, now careful, do not write this as the log of 30. It's not the same thing. It's two separate logarithms. So here's where our calculator can be put to use. We can find what the logarithm of 60 is, divide that by the logarithm of 2, and we get a value of around 5.908 or so. So that's saying 2 to the 5.908 equals, actually is about equal to 60. All right, so this is why we even have logarithms, to solve problems where your variable is an exponent. So we're going to see a bunch more of those today, like this one. We need to solve this equation. E to the x power minus 7 equals 12. Now just a warning for you. Just because you see x as your power here, as your exponent, doesn't mean you should take the logarithm of both sides right away. Instead, what you should try to do is try to get this quantity by itself first. So your first thing you want to do here is get rid of that minus 7. So let's write this as e to the x power equals 19. Now that we have that base, that number to the x power, now that's by itself, now we should take the logarithm of both sides. Now just a hint for you, if you ever deal with equations with e to a power, it's best if you don't use the common logarithm, it's best if you use a natural logarithm. You'll know why in just a bit, but let's take the natural logarithm of both sides, and that'll pull that x out in front. So we can write this as x times the natural logarithm of e equals the natural logarithm of 19. Now what I'd like you to do at this point is to just type this quantity in your calculator, natural log of e. Yeah, if you do that, you get a value of 1. So this is like saying x times 1 equals natural log of 19. Well, x times 1, that doesn't affect the equation at all, so I'm just going to say x equals the natural log of 19, which as a decimal is around 2.94 or so. Now, on your next test, you're going to have a number of these problems. These problems are very, very easy to check. We can take that number, plug it in up here for x. So if you type in your calculator e to the 2.94 power minus 7, hit enter, you won't get exactly 12 because we rounded this down here, but you'll get something very close to 12. So just a word of advice for you on your next assessment. Check your answers by plugging these values back in here in place of x. Okay, let's take a look at another example. Solve 5 times e to the 3x power plus 4 equals 10. Now, similar to the last example, you want this quantity to the power by itself. So let's subtract 4 from both sides. And then let's divide both sides by 5. Let's get rid of that 5 as well. So we have e to the 3x power equals 6 over 5, which is the same as 1 and 2/10. So again, we've got our variable up here. Guess what? There's nothing we can do about that 3 right away. So let's take the logarithm, and actually I'm going to use the natural log of both sides, which will allow us to pull this entire power, 3x, out in front. So we get 3x times the natural log of e equals the natural log of 1 and 2/10. Now we know natural log of e is equal to 1, so I can write this as 3x equals the natural log of 1.2. Now, just like in algebra, if you have 3 times something, you get rid of that 3 times by dividing both sides by 3. Careful. We're not just dividing 1.2 by 3, we're dividing the entire quantity by 3. So now we can say, hey, x is going to be equal to this quantity here. If you type that in your calculator, you'll get something around 0.061. So x is about 0.061. And again, we can test it by plugging it in up here in place of x. Okay, let's take a look at one more of these exponential functions. This is the most complex one we've seen so far, and this actually goes back to our Algebra 2 days. So to solve this, I'm going to think back to a similar Algebra 2 problem. So let's just separate our page for now, and I want to write for you this equation. Y squared minus 7y plus 12 equals 0. Now when you solve these back in your Algebra 2 days, what you learn to do is to factor this expression as y minus 3 times y minus 4. Then we could set both parts equal to 0 and solve both of these for y. And we get our two answers. Now I want you to look and see how similar this equation is to this equation over here on the left. What we're going to do is solve this the exact same way. So what we're going to do is factor this as e to the x minus 3 times e to the x minus 4 equals 0. And then just like before, we're going to take each of those parts and set it equal to 0. On the left, if we add 3 to both sides, we get e to the x equals 3. We can then take the natural log of both sides. That will move this power out in front, which is what we want. And we can write this as x times the natural log of e equals the natural log of 3. Natural log of e is just equal to 1, so we know x is going to be equal to the natural log of 3, which is about, I don't know, that's about 1.0986 or so. Let me finish this one here. So we can say e to the x equals 4. Taking the natural log of both sides and moving that x in front gives us x times the natural log of e equals the natural log of 4. Natural log of e is equal to 1. So there's our value of x, which is about equal to 1.386. So if you can do this problem in Algebra 2, you can do this similar problem in Precalculus now. You get 2 solutions in Algebra 2, you get 2 solutions in Precalc. Let me give you a warning before we move on. Every once in a while in Algebra 2, you get a solution that just doesn't work. You plug it back in, doesn't quite work for you. With these kind of problems, that happens actually fairly regularly. If you take one of these answers and plug it in up here for x, you'll get something that just doesn't work. So keep that in mind, that we do want to check your answers, make sure they work before we move on. Okay, so that is just a variety of different exponential equations that we can solve using logarithms. So keep this in mind. If you ever see a number to the x power where your variable is in the exponent, you're probably going to use logarithms to solve that equation. So exponential equations require the use of logarithms. Now we're going to see some logarithmic equations. To solve logarithmic equations, these are going to require the use of exponents. So this fifth example here, solve log of x equals 2. It looks very, very difficult. How on earth are we going to solve this? If you ever have a logarithmic equation, let's solve it by writing it exponentially. So the first thing I want you to do is think of the base here. The base is 10. And let's convert this. So 10 to some power equals x. And there's your power. So 10 to some power equals x. Now look how simple this is when you rewrite it this way. You've got your answer already. X equals 100. So if you have logarithmic equations, rewrite them exponentially first. So rewrite it like this first. Once it's written this way, it's pretty easy to solve. So keep in mind, if you have an exponential equation to start, you're going to use logarithms to solve. If you have a logarithmic equation to start, you're going to use exponents to solve. So let's look at one last example, then we'll call it a day. So this one says solve 7 times the natural log of 2x equals 10. And the first thing I want you to think about is, what is that base? That base is e, so I'm going to write it in here. Now do not try to rewrite this right away. Instead, you want to try to get this natural log by itself first. So let's divide both sides by 7, which gives us the natural log of 2x equals 10 over 7. Now since it's the log of 2x, we can't get rid of the 2 quite yet, so let's rewrite this exponentially. So we're saying e to some power equals 2x, and there's your power. So e to some power equals 2x. Check it out, we've almost got this. E to the 10�7ths, your calculator can do. Divide that quantity by 2, you've got the x by itself. So x is going to be equal to whatever you get for that, e to the 10�7ths power, and then divide that by 2. If you do that, you'll see that you get a value of about 2.086 or so. Again, you can check it by plugging that back in here in place of x to make sure that it works. Okay, so keep in mind, if you have an exponential equation, like for example, if you have something like e to the x power equals, etc., use a logarithm to get that x out of the exponent. If you have a logarithmic function like the natural log of x equals, etc., here's where you're going to use an exponent to solve this for x. Okay, let's practice some of those. There's an assignment on page 221. Practice some of these exponential and logarithmic equations before moving on to your next set of notes.